screen.
Yeah. Okay, should I go?
Okay. Andrew Dessler is a professor in the Atmospheric Science Department at the Texas A&M University and director of the Texas Center for Climate Studies. And he's here to talk about a quantification climate change drives increased energy demand and energy cost. All yours, Andrew.
So thank you. It's a real pleasure to be here at this meeting. And I'm going to talk about energy and climate change. So this is a plot of the population-weighted Texas temperature. I got this from ERA5. And what you'll notice is that there's a warming trend. And so you expect this, as temperatures go up, to increase energy demand because people have to run their air conditioners more. And so the goal of this talk is to try to quantify this and figure out exactly how much more dollars are escaping from people's wallets in response to this. And so the way we're going to do this is, first thing we need to do is come up with a relationship between temperature and demand. And so luckily ERCOT gives us demand. You can just download that. And I'm going to get temperature again from ERA5. And then I'm going to regress them. And this is basically what the plot looks like. So it actually is a reasonably tight relationship between daily average demand and daily average temperature. And then we're going to fit this with a fourth order polynomial fit. And so once we have this relationship, we can take the temperature. So we have daily average temperature from ERA5, and we just plug it into the fit. And then from this, we can come up with demand for any time period. So the plot on the right shows what electricity demand would have been in 2023 had the temperatures from the year 2000 occurred. So again, the important thing to understand is I'm making predictions of demand. Everything is the same as 2023 except the temperature. So the same population, the same energy intensity, the same mix of economic activities, everything's basically the same. The only difference is the temperature. If you took the temperature for a prior year and plugged it into 2023, what would the demand look like? And so again, I can take the entire temperature time series going back to 1950, and I can calculate what the demand would have been over this time with everything the same as 2023 except the temperature. And then what I'm going to plot next is the relative demand relative to the 1950 to 1980 baseline. So the average demand over 1950 to 1980 is 0. And then, and this is the demand relative to that. And what you'll notice is that there's a trend, and this trend is due to climate change. Temperatures are going up, and that's driving an increase in, and this is annual average demand. I should say that the scale on the left is gigawatts, the scale on the right is percent. And so you see that sort of by the end, by the 2010s, we're a few percent of energy demand higher than it was in the middle of the 20th century. So you see this long trend due to climate change, and then you also see year-to-year variability. And this is essentially most of it's unforced variability. There might be some other stuff in there. But I'm going to separately evaluate the differences due to the long-term trend, climate change, and due to year-to-year variability. And so this is what the numbers are. So if we ask, how did electricity demand in 2023 change compared to the middle of the 20th century, we see that energy demand is about 5% higher, 4.6%. And that was about 40% due to climate change and 60% due to variability. And if you're interested in how I do that, technically ask me. I'm not going to go into how I split those up. And that corresponds to about 2 gigawatts of additional demand. So that's a fairly large amount of demand. And we can look at this by season. And, you know, I would point you to the summer. So the summer of 2023, electricity demand was 11.6% higher than the middle of the 20th century. it was hot. It was hot and people were running their air conditions. And that was, again, about 40%, maybe 30% due to climate change and 70% due to variability. It was just a really hot year. And note that's about almost 7 gigawatts of average additional demand. That is an enormous amount, and I'll talk about that in a second. But the bottom line here is that this is going to drive up costs just by itself. If you're consuming more electricity, you have to pay for every additional kilowatt hour. And so your first sort of naive estimation of the economic impact of this is that people are going to spend, for the whole year, 4.6% more on electricity than they would have without, without climate change plus variability. Now, that's not a complete picture, though, because the way the ERCOT grid works, as demand increases, the price also increases. And that's because everybody pays the price of the most expensive power that ERCOT has to use to satisfy demand. And so as demand goes up, ERCOT is pulling progressively more expensive assets into their energy mix. So the price goes up. And so you can see that on this plot. The x-axis is average daily demand in gigawatts, and the y-axis is the wholesale price. This is Texas average, and the wholesale price is the demand-weighted daily average. So you can see that there's a dog leg in it, and below about 60 gigawatts, the increase of price with demand is just because they're pulling in more expensive producers. And then you see it suddenly shoot up at about 60 gigawatts of daily average demand. And that's when you start getting congestion on the grid and you start reaching limits in how much generation is available. And at that point, ERCOT cranks up the price to try to incentivize people to stop using so much power. And just to give you an idea of how big a deal this increase is, remember I said that during the summer, demand went up 6 gigawatts on average. And that's the difference between paying $36 for a megawatt hour and $80 for a megawatt hour if you go from 58 to 64 gigawatts. So that is a big increase in cost. That's much larger than so I'll explain that a little differently. But that is a big increase in cost. That's more than doubling the cost per megawatt hour you're paying. So again, the important thing to understand is not only are you buying more units of energy, but you're paying more for every unit you buy. All right, so now what I can do to estimate the total cost, I take the population weighted temperature in the upper left, I plug that into the fourth order fit. That gives me the daily average demand in the upper right. And then I take the daily average demand and I plug that into the fit, which is the orange line I get from 2023 demand versus price data. And I can come up with how much we're paying for every gigawatt hour of power. And then you just multiply price by demand, you can get the total cost. And so this is basically what the percent change in the total cost of wholesale energy. So I'll talk about what wholesale energy means. And this is sort of for 5 years. You can kind of see there's a lot of year-to-year variability. But a few things to notice: winter costs are declining. That's what you'd expect. Warmer temperatures mean you have to run your heater less in the winter, so you're paying actually less money in the winter. The exception, of course, is 2021. We had Uri. We paid a lot of money that week, and you see that it's an outlier in the winter. The other thing to notice is the summer costs are increasing because people are running their air conditioner more, and it's a big increase. 2023, the combination of increasing demand and increasing price means you are paying 130% more than we would have paid on average in the middle of the 20th century. So that is a big increase. And you also see the annual costs are increasing. And what that means is that the decrease in winter costs are not canceling the increase in summer costs. The increase in summer costs dominate because we consume so much more power on average in the summer than we do in the winter. It's just, we are, winter costs are the ones that are really driving, or summer costs are the ones that are really driving the boat here. And so to
2 minutes.
Okay, so I'll just to sum up, I'm almost ready to sum up here. This is 2023, and the first column shows how much the percent increase compared to the middle of the 20th century. The second column is how much of this is climate change, and the third column is how much of this is climate variability. And so you see that 2023 we consumed much, the cost of wholesale energy was much higher than it was in the middle of the 20th century, but most of that was due to variability. But a lot of it was due to climate. This is not insignificant. And that's mainly in the summertime. Now, let me just emphasize that this is the change in cost of wholesale energy. The total cost of the economy is probably lower because only about 75% of the power that Texans or that ERCOT serves is sold through the wholesale market. Other ones are sold through bilateral agreements between load serving entities and generators. And it's likely that those didn't go up as much as the wholesale price did, but that's kind of an unknown. So just to sum up, climate change is costing us money in many ways, but in electricity in particular. And increasing temperatures hit us two ways. They increase energy demand. So we're buying more units, kilowatt hours of energy, and it increases the price. We're paying more for every kilowatt hour. 2023 saw demand increase on average by 2.2 gigawatts, and in summer by almost 7 gigawatts. That's enormous. Now, most of that was variability, but about a third of it was climate change. And this increased the total economic cost of energy on the U.S. by about, or on the Texas by about 40%. If you work out the total dollars, it works out to, it's kind of hard to do this exactly, but $170 a person is kind of an estimate of how much additionally we paid for electricity in 2023. And that's mostly from the increase in price, not from the increase in the number of units consumed. So thanks for the invitation. I'd be happy to answer any questions.
Thank you, Andrew. We have some time for questions. Please raise your hands or write it down in Q&A. Well, I have a question myself. I moved 1 year ago to Austin, and what I'm seeing is that many houses are not well prepared. At least the rent houses are not well prepared for keep warm the house during winter or keep it cool during summer. And I was wondering, there is any study that calculate how much this kind of changes in the house conditions might affect to the electricity demand?
Yeah, well, certainly that's a big issue, and it certainly was during, Uri, because the worst houses tend to be the people that are the poorest. So as soon as the power goes out, those are the houses that plunged in temperature the fastest. I don't know any studies that have been done on that, but clearly, building codes are a way to decrease energy usage, energy efficiency. Sort of any energy efficiency would do that. Is certainly, I think, that's the kind of thing we need to really think about, or we're going to be spending a lot more money on electricity.
Thank you. Any other question for Andrew? Okay. Vanessa, you can formulate your question. Oops. Sorry. But you need to unmute yourself.
Yes. Hello. Maybe you had said this earlier, and I missed it, but how do you account for the change in population since the early 90s, 2000s to now in terms of cost increase and demand with energy?
Right. So I'm keeping everything in 2023 fixed and just asking the question, what if we had the temperatures from a previous period? So the population is the same. The infrastructure is exactly the same. The number of electric heaters are the same. The number of heat pumps are the same. Everything's the same. I'm just saying, if we took 1950 temperatures and brought them up here and 1990 temperatures and 2023 temperatures, how does the demand change? So the idea is, this is how much climate change is costing us, because 2023 is what it is, and but we're modifying the climate.
Thank you.
Okay, thank you, Andrew.